Hello class, in this video we're going to be discussing annuities. I wanted to start by getting into the concept of what an annuity is, working into the math of how we can solve, say, their present and future values. Now I wanted to warn you before we begin, the derivation of the formulas that are in the packet are a little bit lengthy, but important nonetheless. And that's kind of what this video is about. Um, Looking into the math of why those formulas work. And so in the next couple videos, we'll be looking at examples and we'll do some number crunching, just kind of the TLDR, what's the answer? But you know me, math always needs to be rooted in something sensible, and so that's our goal here. So let's start with the slides, and I'm going to just walk through the derivations of the formulas. So before we get into it, an annuity is just a series of fixed payments. Like for example, say every month you're going to put $200 into your savings account over and over and over again. That would be an idea of that. And over time, that value will be the amount in your account grows and grows and grows. Now, the other implication of an annuity is that there's going to your savings account will also be generating interest, compound interest based on either monthly or yearly. Again, you can do it however you want to. Typically, monthly is how it will work in a lot of real annuities. Um, but notice that the payments must be the same amount to be considered a true annuity. Though technically, if you're varying the amount that you're putting into your account month by month, that's still like an annuity. It's just you can't use these formulas because these formulas are solved for a series of fixed payments to be the same every single time. Also, over a predetermined time frame is important as well. And another, just a technicality to mention before we get any too much further, is the book distinguishes um, different types of annuities by the amount of the first payment, um, and it can cause annoyances in those calculations. So let's move to the next slide. It's not working for some reason. There we go. Moving to the next slide. Wanted to define how our book distinguishes. Well, is the first payment going to be made exactly today or will it be made after 1 month? Because that's the whole deal. Like when we talk about sequence and series, you could have a sub 1. Is that the first term of my series or is it my current amount? Because as we described, there's always every sequence or series has a term 1, but a lot of times we could use a term 0 instead to say, well, okay, current initial time after 1 month, that would be our first term, and so on. So basically, to iron out the details, the book always assumes we're dealing with ordinary annuities whenever it's talking about it, not an annuity due. So what is that? An ordinary annuity is an annuity where the first payment is scheduled in the first month. So like if we're imagining it on a graph, I took this from the book because I thought it was pretty good. Um, Here's our current time, month 0. There's currently we're not putting any money in, but in 1 month that will be our first payment into the annuity, and so on, and that would be what we call an ordinary annuity. Where an annuity due is an annuity where the first payment is due right now, and we're going to have a total of n payments throughout. So it starts immediately, which is a little bit different in terms of the timeline, but you can just generally throw this out the window. But a lot of the formulas we're doing with just a slight input, a slight difference to the input variable would fix that if we wanted to adjust them for annuity dues, but we're going to do them for ordinary annuities. So let's get into what's the present value and what's the future value of annuity. Now this is the derivation that takes a little bit of time, but they're very similar to one another. So let's get right into it. So the present value, the net present value is just the sum of all the present values of the annuity. So if we're thinking about that series of payments and applying what we discussed or what was in the previous video about present value, the present value of each of those payments should actually be less and less and less because the further and further the payment is down the annuity, the smaller the current value or the present value of that particular payment. So it's like if I wanted to know, well, what the sum of all of those payments, what's the present value, I would want to add up all of that. And each of those present values is given by the present value formula, which is the same thing we're using, which is the future value times 1 plus the periodic interest rate to the minus n power. Um, Oh, my dog says hello. I don't know if you could hear that. But so in the context of annuities, you might notice R as the capital variable in front of for the future value. That's just what the book uses. I'm gonna use the same notation in my notes to not try to not be too confusing. But basically, you're gonna take each payment is the amount of the future value. And then it's going to be multiplied by 1 plus the periodic. Also, the book uses R for its periodic interest rate, whereas I use P. So notice in my formula down here, I'm using R times 1 plus P to the minus 1. And basically, the first payment after 1 month should have a present value to the minus 1 power because it's 1 month removed. And that's kind of what this diagram is helping us to visualize as well. The present value of this was 1 month because it's now. What's the value right now? And this payment is knocked back 2 months, 3 months, so on. So the value of the entire annuity is the sum of all of the present values of the annuity from the first month to the nth month, which is the final. Um, and I'm going to use capital N for my nth month because that's consistent with the N from the packet, which is where, as I mentioned before, little n is what the book uses for the number of total payments, which I don't. So, anyways, but basically there's some math that we can do in here, and that's where we go to the next slide. So in the next slide, basically there's a simple formula for figuring out the present value of an annuity, which the book uses A, as does my notes, because I'm trying to be consistent, for the present value of annuity. I don't know. We could just use PV but A for annuity, and this is describing its present value. So what the slides say is note that this series is a geometric series because if I'm kind of paying attention to it, it's a sum of a bunch of different things. Like we could imagine this as 200 times 1.01 to the minus 1, 200 times 1.01 to the minus 2, and so on. Notice that like if I was actually plugging some numbers in, the first term of the sequence or the series would be this, and each consecutive term is the same thing, but it's multiplied by an additional 1 plus p. Well, technically divided because it's negative, but each one has an additional division by 1 plus p. So what this is implying is that it's a geometric series, its first term is this, and its common ratio is this. So if you go back to our notes on geometric series back in chapter 1, I know it's been quite a while, but remember that I'll go ahead and note the formula on my whiteboard because I'm probably going to be using it. But the formula for a geometric series is an is equal to ar to the n minus 1. And you can't see it because it's over here. But that's, a general geometric series, which just means it's a sequence or a series where each term is being multiplied or divided by something. So basically, if we're looking at that one, the first term, let me move this over on my whiteboard. The first term was r times 1 plus p to the minus 1. And so that would be that. And then r was equal to 1 plus p to the minus 1. Because each term was divided by an additional 1 plus p as the common ratio. And why am I getting into all that? It's because I could rewrite this as in a compressed form and simplify. Basically, there's some algebra I could do to make this look a little bit cleaner. But that's what I have next. So I'm trying to walk you through what the math I'm doing in the slides because it is not necessarily obvious as well. But basically, next I said that the value of the annuity is equal to A times the sum of all the terms, 1 plus B that. Because this is really just a sum of a geometric series. And so I've written it in exactly that form. This is R to the n minus 1 power. Also, notice that I've used I as a subscript of the series notation instead of n because n is already in use in my formula. So a lot of times we use I or k for the dummy variable within a sequence or series. But if you think about what this will do is the first term I'll plug in, sorry, let me put my laser pointer on. The first term will plug into there. So this will give me this times 1 plus p to the minus 1. And I've just now realized that this actually should have a minus 1 on it because it should start with the 0 term. But then the or I could start at the zero term, which would be fine. It doesn't really matter, which makes me wonder why I'm actually getting into this. But some of this stuff is in the book, and I think it's important to review a lot of the math we've talked about and why this makes sense. But anyways, if we then plug in 1 and 2 and 3, what we'll see is we're going to take this and multiply by more and more of these. Actually, we could amend this. I can fix this just by removing this. I don't really need that, and this should be perfectly correct. Because I'm going to start with r. I'm going to start by multiplying by one of these negatives. Then the next one is 2. It's 1, then 2, then 3, then 4. And this, what the summation means is just add all of those things up by plugging in everything from 1 to n into the formula. But anyways, this is, excuse me, this series is geometric, which has a very important conclusion. So this is something that we didn't actually get to when we were back in 1.6. So now is a good time to go back into geometric series. But it turns out that geometric series have a simple shortcut for finding the sum of a finite series. And all that means is that if I want to find the sum of this annuity, there's actually a really simple fraction that I could write to get the answer, which wouldn't necessarily be obvious if you had not seen the math before. But returning back to geometric series, what I wanted to mention is if we have a generic geometric series like the formula that I wrote on the whiteboard, the nth partial sum of the geometric series is always given by this formula. And this formula was back in 1.6. Some of you guys used it in your homework as opposed to using your calculator to do sums of series, but it was something that I didn't necessarily want you guys to do because we hadn't gotten there. But all that means is that if we add up, so for example, applying this to finance, if we have an annuity with say 36 payments, we want to figure out, well, what's S sub 36? What's the sum of the 36 payments? Like in the case of A, the annuity, we want to find what's the sum of all of those present values, which would give us the present value of the annuity. And basically that can be plugged into this formula to get the answer. But one of the questions is, why does the geometric series have this particular sum, and why does this make any sense? So what I wanted to walk you through is there's a simple proof of this geometric series that was discovered quite a long time ago, and that will be in the next video.